Newton's second law can be defined like so. When viewed from an inertial reference frame, and I'll describe what this means in a minute, the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. Okay, let's explain what this means with an example. Imagine we have a hockey puck that is currently at rest on the frictionless surface of an ice rink. Now, friction is not going to be exactly zero here, but we can ignore this for now to make our free body diagram a bit easier to understand. So a couple of seconds later, two hockey sticks strike the puck simultaneously and exert two different forces on the puck. One of these forces is in the positive y direction and the other in the positive x direction. Now, using vector addition, we can sum these external force vectors to obtain the net force exerted on the puck. Now, the acceleration of the puck is proportional to this net force, and the larger the net force, the higher the resultant acceleration will be. We also intuitively know that if the puck had a higher mass, the same net force would not accelerate the puck as much. In fact, the acceleration would be inversely proportional to the mass. Newton's second law mathematically looks like this, where the sum of all the external forces acting on a free body, and in this case the free body is our puck, gives rise to the acceleration of that free body. And this is a cause and effect relationship. And also notice that the net external force and the object's acceleration are both vectors and always point in the same direction. Now, coming back to the part where our definition states, when viewed from an inertial reference frame, an inertial reference frame is simply a coordinate system that is not accelerating. So let's imagine instead of ice hockey, we're playing air hockey inside a train carriage. If our train carriage is not moving, or is moving at a constant velocity, our coordinate system is an inertial frame because our unique coordinate system inside the carriage is not accelerating. In this case, Newton's second law holds true. However, if our train starts to accelerate, all bodies within our coordinate system will start to experience a fictitious force that seems to push in the opposite direction to the acceleration vector. In this situation, we're dealing with a non-inertial reference frame, and Newton's second law would need to be amended to account for the acceleration of the frame itself. You'll cover this later when looking at how to apply Newton's laws to objects travelling in circular paths and other accelerating reference frames. So let's finish with an example question that utilises Newton's second law. So we have our hockey puck again, and it's at rest on a flat frictionless surface. A second later, it is hit simultaneously by two hockey sticks that exert two separate forces, F1 and F2, as shown in the diagram here. F1 has a magnitude of 5 newtons at 20 degrees clockwise from the x-axis, and F2 has a magnitude of 8 newtons at 60 degrees counterclockwise from the x-axis. Now, if the puck has a mass of 0.3 kilograms, determine the magnitude and direction of the puck's acceleration. Okay, because the acceleration and forces are vectors, and we're working on the 2D plane, we can resolve these vectors into their x and y components. In other words, we can apply Newton's second law separately to each axis. So let's first analyse the net force acting on the puck in the x direction. So we can draw two right-handed triangles here, where the hypotenuse is the forces acting on the puck, and the horizontal and vertical lines are the x and y forces respectively. So the net force in the x direction is the summation of the F1 force and the F2 force in the x direction. With these right-handed triangles, we can use a bit of trigonometry to work out the net force in the x direction. So we have F1 cosine minus 20 plus F2 cosine 60. And all we're doing here is adding up the adjacent sides of both triangles here. And we end up with a total net force in the x direction of 8.7 newtons. So now if we look at the net force in the y direction, we add up the opposite sides of both triangles and we get F1 sine minus 20 plus F2 sine 60, and the total net force in the y direction is 5.2 newtons to two significant figures. With these x and y net force components, we can rearrange Newton's second law and find the puck's x and y acceleration. So the acceleration in the x direction is equal to the net force in the x direction divided by the puck's mass. And we get a value of 29 meters per second squared. And in the y direction, the acceleration is equal to the sum of the net force in the y direction divided by the puck's mass. And we get 17 meters per second squared to two significant figures. So we can draw another vector diagram now of the accelerations in the x and y direction, with the hypotenuse being the resultant acceleration vector for our puck. And we can use Pythagoras' theorem to find the magnitude of the resultant acceleration and use trigonometry to find the angle relative to the x-axis. It's also really important to notice here that the resultant acceleration vector points in the same direction as the net force, and the acceleration's magnitude is dictated by the puck's mass. So in other words, a higher mass will reduce the size of the puck's acceleration, but if the puck was much lighter, the acceleration would be larger.